Hello everyone. Today I'm going to give you a quick introduction to neural networks, what they are, how they work, and why they are so powerful. Let's get started. So what exactly is a neural network? A neural network is a computational model inspired by the human brain that learns patterns from data. Here are the key characteristics. Inspired by the brain. Artificial systems designed to process information like biological neurons learns patterns automatically. Unlike traditional algorithms, neural networks discover patterns through layers of connected neurons. Adaptable. Can classify images, predict stock prices, recognize faces, all with the same architecture. Powerful for non-linear problems. Excels at finding hidden patterns that traditional algorithms miss. This flexibility makes neural networks one of the most transformative AI technologies today. To understand that better, let's look at the architecture. Here's what a neural network looks like. Input layer, left, where data enters. 3 neurons in this example. Hidden layers, middle, the thinking layers with 2 neurons each. In real networks, these can have hundreds or thousands. Output layer, right, produces the final prediction. Notice the lines connecting neurons? These are connections, each with a weight. Data flows left to right through forward propagation. This architecture is called a multi-layer perceptron (MLP), one of the most fundamental neural network types. This architecture has key components. Every neural network is built from 4 essential components. First, neurons, basic processing units that receive inputs and send outputs to the next layer. Second, weights, connection strengths between neurons. These learnable parameters are adjusted during training. This is how the network learns. Third, bias, offset values that allow neurons to activate independently, giving the network flexibility. Fourth, activation functions, mathematical functions that introduce nonlinearity. Without them, even deep networks would just perform linear transformations, unable to solve complex problems. Together, these components enable neural networks to learn complex patterns. Weights and biases are updated during training. Activation functions remain fixed. Now, how does data move through this network and how does it learn? Forward propagation is how trained networks make predictions. First, input data enters the input layer. Second, each neuron computes z is equal to sigma of weight times input plus bias. Third, apply activation function. Output is equal to f of z. Fourth, pass output to next layer. Repeat until output layer. Backpropagation is how networks learn. First, forward pass. Predict using current weights. Second, calculate error. Compare prediction to actual target. Third, backward pass. Work backward, computing how much each weight contributed to the error using calculus. 4. Update weights. Adjust weights using gradient descent to reduce error. This process repeats many times. With each iteration, predictions improve until the network converges. This is learning. A critical part involves activation functions. Three common activation functions. ReLU. F of x is equal to max of 0, x. Most popular in modern deep learning. Fast and effective. Sigmoid. F of x is equal to 1 by 1 plus e to the power minus x. Outputs 0 to 1. Useful for probabilities. Tanh. F of x is equal to e to the power x minus e to the power minus x divided by e to the power x plus e to the power minus x. Outputs minus 1 to plus 1. Centered at 0 for efficient training. Why needed? Without activation functions, even stacking many layers would just perform repeated linear transformations, mathematically equivalent to one transformation. Linear functions cannot solve nonlinear problems. Activation functions introduce nonlinearity, the power of neural networks. Without them, you just have a glorified calculator. So we understand how they work. Where are they actually used? Neural networks are used everywhere. For image recognition, in object detection, facial recognition, medical imaging, etc. In natural language, for machine translation, conversational AI like ChatGPT, sentiment analysis, etc. For predictive analysis, in stock forecasting, demand prediction, fraud detection, etc. In autonomous systems like self-driving cars, robotics, drone navigation, etc. The versatility is remarkable. You can even adapt a trained network to new tasks using transfer learning, making them more powerful and cost effective. Let me bring together the main concepts. 5 key concepts to remember. First, layers matter. Input, hidden, output. Greater depth allows more complex pattern learning. Second, weights and bias. Learnable parameters updated during training. They encode learned patterns. Third, activation functions, essential for nonlinearity. Without them, complex learning is impossible. Fourth, backpropagation, the training algorithm that efficiently adjusts weights to reduce error. Fifth, versatility, works across vision, language, time series, robotics, and beyond. These five concepts form the foundation of modern artificial intelligence. That concludes our overview. Thank you for your attention. We have covered architecture, training, and real-world applications in just 5 minutes. Neural networks are a vast topic. There's much more to explore, but you now have a solid foundation for understanding how they work and why they are powerful. I'm happy to answer any questions.